Okay, welcome back to the lectures, everyone. So we are finally coming to an end of characterizing the complexity of infinite hypothesis classes. So last time we talked about Rademacher complexity. We talked about growth function. And finally, we introduced the VC dimension. Today, we will see a few examples of how to come up with or characterize the VC dimension of a bunch of hypothesis classes that are commonly used in machine learning applications. Okay, we'll see how, basically through seeing these examples, we'll see how we can use a lower and upper bound to characterize VC dimension of any hypothesis class. Hopefully this is helpful for our practical uses. All right, so again, just to remind everyone, definition of the VC dimension of a hypothesis class, H is defined as the size of the largest set that can be fully shattered by H. Okay, again, remind everyone what it means by shattering. A set S, of course, more than 1 point in the S. So S is just a sample. Now, the set S is set to be shattered by a hypothesis set H when H realizes all possible ways of labeling the points of S. So basically means that, the pi H of M is actually 2 to the power M. Okay, so remember what is pi H of M? The growth function, right? The maximal ways how the hypothesis can label the points in a set. So it's the growth function. So as long as, the growth function for M is equal to 2 to the M, then we can say it's fully shattered, right? Well, now what is the definition of the VC dimension? VC dimension means it's the maximal M such that the pi HM equals to 2M. Okay, so this might be a little bit confusing, but very importantly, here are some interpretations. If VC dimension of H is D, then there exists a set of size D that can be fully shattered by H. And the existence is very important, right? It doesn't mean that everything will be shattered or every set of size D will be shattered, right? It's talking about its existence. So this argument is wrong, as we discussed last time. All sets of size D or less are fully shattered by H is not correct. However, because of this, we come up with a way of compute VC dimension. We talked about a lower and upper bound. So what is a lower bound? A lower bound of VC dimension, basically you wanted to show a set of size D can be shattered by H. So as long as you see, you show an existence. So this at least is a lower bound of the VC dimension, right? But more importantly, and a little bit more difficult, is to show the upper bound of VC dimension, which is a little bit more challenging. It's like no set of size D plus 1 can be shattered by H. Right? This is talking about the unrealizability. So, is there any confusion so far? If not, then we'll see a few examples and basically showing how we compute the VC dimension using this lower and upper bound. Again, I wanted to emphasize the lower bound is a set of size D that exists that can be shattered by H. Not necessarily all sets of size D can be shattered by H, okay? Well, however, the upper bound is harder for some scenarios because it has to be like no set of size D plus 1 can be shattered by H, okay? So by the way, do people have confusions about why I have this lower and upper bound for computing VC dimension? Don't be shy to, speak up. Any confusions? Well, feel free to discuss. Okay, so if no further questions, comments, we'll proceed. So we'll see a first example. Everyone has been working with lines, real lines, intervals of real line. So this VC dimension example first, the first example, the VC dimension characterization, we look at an interval of the real line. So what does this mean? This means that within the interval of the line, every points that are falling within the interval of the line will be labeled, let's say by +1, and everything outside of the interval of the line will be labeled by -1, or vice versa, right? Everything within is -1, or everything outside is +1. So, those both are fine. So this is so-called the H, right? So H include every possible interval of the real lines, okay? So is H clear here? It's apparently infinite, right? If you wanted to count the cardinality of H, it's infinite. But let's see how complex this kind of hypothesis is. Okay, so what is your observation? You can see the first observation here is that any set of 2 points can be shattered by 4 intervals. So what does that mean? So now look at these two points, this one and this one. Can you see my cursor from the screen?
Yeah.
Okay, wonderful. So just want to make sure, you see this dot here, right? This is the first point. This is the training data set 1. Sorry, training data example 1. And this is your training data example 2. Now, just imagine if you have a hypothesis in hypothesis class, which is this one, let's say. Okay. Then how would you label the 2 points? You would label this as positive and this as negative. Why? Because this dot will be within the interval of this line, and this dot will be outside of the interval. Do you see? So focusing, okay, I don't know if I'm confusing people. So we are focusing on this line here. Okay, for visualization purposes, they are not exactly, on the same, horizontal line, but pretend that they're on the same horizontal line. We're only in the one-dimensional space here. Okay, so this is your hypothesis. So this is your H within H. Okay. Now, do you see what I mean? So, for this example, it is within the interval. So this example will be labeled as +1 by this hypothesis H. Oh, actually, let me call this H1, okay? So it's gonna be H1. H1 of X1 will be +1. And this dot will be H1 of X1 is gonna be -1, right? So basically for H, you've able to label you've been able to label it as plus and minus. Okay, so that's for H1. Sorry, this is H1. Is this clear? Okay, let me erase this. Now let's look at another one. This is H2, let's say. Okay, so for H2, are you going to label X1 as what? Do you agree? You're going to label, X1 as -1 and X2 as +1. It's very quiet. So, maybe you can give me some feedback so I know, we don't have a problem and we can proceed.
this makes sense so far.
Okay, okay, thanks. Well, so now we can look at this one. This is your H3. How would H3 label these 2 points? -1 and -1, because these two, both of these 2 points are outside of H3. Well, now, you know, very obviously, you see where I'm going. H4. Now this H4 is going to label these 2 points as +1 and +1. Okay, so what this means is, you know, so how many ways you can label x1 and x2 since your m is 2 here? 2 to the power m, right? Which is 2 to the 2, which is 4. So you can shatter all possible, so this is a shattering, right? You can cover all possible labels using your hypothesis class H, right? So what does this give you? This gives you a VC dimension lower bound. Okay, I hope this is very clear. Now, so you know, because we find such a data set, we find such a sample, you know, which is a data set, which is these 2 dots, well, m equals to 2. So we know that the VC dimension of interval of the real line is gonna be upper bounded by 2. Okay, so VC dimension of real line is gonna be upper bounded by 2. Lower bounded by 2, sorry about that. It's gonna be lower bounded by 2. So now we think about the upper bound. So what is the upper bound? The upper bound of the VC dimension basically means, it basically requires that you cannot find such a set so that it can be fully shattered by H, right? So as long as it's D plus 1, you find such a set with D plus 1, it cannot be fully shattered by H, okay? So now the point here is that if you're looking at 3 dots, right, then no set of 3 dots can be shattered since the following dichotomy, +1, -1, +1 is not realizable, right? Once you have such like 3 dots, right? So in order to have a full shattering, you need to make sure that you can find, such a hypothesis, you know, you wanted to making sure that your hypothesis can realize all possible ways of labeling these 3 points, right? So one way of doing that, of course, is plus minus plus, right? That's just one way of doing that out of the 2 to the power 3 ways of labeling these 3 points. One way is that, and you know that no line, or basically no interval of the line could really realize such a dichotomy, plus minus plus. So this means you find an upper bound of the VC dimension. And that's why the VC dimension of intervals in real space, intervals in real line here, this is 1 here, so it's real line. Intervals of the real line, the VC dimension is just 2. Okay, so I'm going through this example very slowly because I think this is the first time we're seeing how to characterize the VC dimension using an example. So I'm going through it very, very slowly. Hopefully everyone can follow this. If so, then the examples later, I'll go through them a little bit faster. So, this is a good time to ask any questions you have.
Is the VC dimension here, you said it was upper bounded by 3?
Right, no, so this is, you can, so D is gonna be a lower and an upper bound. What this means is, if you can find a set of size D that can be shattered by H, and also you can making sure that no set of size D plus 1 can be shattered by H, then the VC dimension is gonna be D. Okay,
that makes sense.
That's a good point. Okay. Any other questions?
Yeah, I have a question.
Yeah, go ahead.
So for this specific type of hypothesis, it is easy to see, that we can apply the same reasoning to say that our hypothesis class cannot shatter a set of size 4, 5, 6, or any number like that. But how do we know in general that for any hypothesis class, if we can't say shatter any set of size 3, then we can't shatter any set of size bigger than that?
Yeah, so that's why if you wanted to characterize VC dimension, sometimes it really involves a lot of thinking, and it's not very easy, although it's not like infeasible, right? But other than VC dimension, there are other concepts, other complexity that are commonly used in machine learning. I didn't have time to cover those. For example, covering number, which is sometimes a simpler argument to characterize than VC dimension. Or there are also other kind of complexities. So if you are curious, you can take a look at those and think about it.
Could you just answer that question by saying your fourth point will be the same as one of the other 3 points, and therefore if you couldn't shatter those 3, now you can't shatter these 4?
Yeah, well, so as long as you cannot find a set of size D plus 1, then your VC dimension shouldn't be greater than or equal to D plus 1. Right? This is a simple logical argument, but if you think about it, if I already cannot shatter the 3 points, then of course I cannot shatter 4. Right? For instance, do you see what I mean? So you have x1. Oh, go ahead.
So you can just repeat the same set of
Exactly.
size 3 you used and add in some arbitrary
Exactly.
point.
For example, you know that with three examples, you cannot shatter plus, minus, plus. Okay. So now, no matter what x4 is, let's say x, you cannot shatter it, right? Because you already cannot shatter x1, x2, x3, which labeled as plus, minus, plus. Does that make sense?
Yeah, that makes sense.
Okay, right.
Yeah, actually,
also, Jonathan is talking about a very good point. A shattering of size n implies a shattering of, a minus 1, and that's correct. Okay.
Can you go back a previous slide real quick?
Yeah.
So here in red, it says all sets of size D or less are fully shattered by H, and that's incorrect. But isn't that exactly what Jonathan just said in the chat?
Oh, it's different, right? So all sets means, I'm not talking about existence. I'm talking about, every possible ways. So actually, I will show you an example later on to show you why this is not correct. Okay.
I got it. Yeah. That makes sense.
Yeah. Good point. Okay. I know this is a little bit confusing, so let's take a little bit of time to think about it. Okay. All right. So can I move on to the next example?
I have a quick question about this example. So on the last slide, it says it's wrong to say that all sets of size D or less are fully shadowed by H. So in this example, it means, I just want to make sure that it means that it's not that any set of, or it's not that any set of 4 intervals can shatter 2 points. It's just that there exists a set of 4 intervals.
Right. It's not
that
very
shatters.
obvious in this example. Reason is, we can't find a counterexample here, but next example is very clear. I can explain that
Okay.
better in the next example.
Okay.
Okay. Can we move on? All right. So the next example is the hyperplane, right? So again, if you have a hyperplane, what is this? Basically a linear classifier, right? So you're like, the one side of a hyperplane, your classifying is positive and the other side is classifying is negative. That's how a hypothesis defines. Then the entire set of hyperplanes is called a hypothesis class of hyperplanes, okay? So now, what is the, so this now becomes a interesting point why, I said not all sets of size D will be shattered. So, here in this example, any 3 non-collinear points can be shattered. So what does this mean? This means that, you can find a lower bound of your VC dimension D, right? So you can find 3 points. As long as the 3 points are non-collinear, then they will be fully shattered by your hypothesis hyperplane. Now notice that if the points are collinear, so let me draw that. If the points are collinear, you cannot find a hyperplane that shatters the 3. Do you see? For example, I cannot realize something like this. Okay? But does this mean that my VC dimension cannot be greater than does that mean that my VC dimension is smaller than 3? Well, I'm looking at the 2-dimensional space here, right? So that's apparently not true, right? So that's what I mean in the first slide. So here, that's what I mean by not all sets of size D or less are fully shattered by H is wrong. In this example, for example, if you find any non-collinear example, non-collinear points in your sample, then it will be fully shattered by H. But if you find collinear ones, it won't. But still, we say it is fully shattered by H because we only care about this existence. As long as there exists a set of size D that can be fully shattered by H, then we say this is going to be a lower bound, right? Is the point clear now?
I have a question.
Yes.
Why can you assume the points aren't collinear? It says VC dimension hyperplanes and RD. Why do you assume the points aren't?
Trying to explain, you only care about existence as long as, you agree that there exist 3 points that are non-collinear, right? You can always find 3 points that are non-collinear. So I only care about existence. That's why I've been emphasizing this point, right? So that not all sets. So let me go back again and we can clarify this question again, okay? So since 3 of you have been asking about this. This is very important. It's talking about existence, right? We're showing a set of size D can be shattered by H, but I'm not saying any set of size D can be shattered by H. That's why we say all sets of size D or less are shattered by H is wrong. Okay? Does that answer your question, Michael?
Yes, thanks.
Okay. Any other confusions about this? And this is very important, right? Okay, so any confusion about why any 3 collinear points can be shattered? Right, so if, you know, this is negative, I can always find the hyperplane of this, right? If this is negative and these are the positive one, I can find a hyperplane like this, right? And if this is negative and these are positive points, I can find hyperplane like this, right? So I can always find a hyperplane that separates the positive and negative points, no matter how you label the 3 non-collinear points. Okay. All right. So, you know, now I hope we've understand why, as long as there exist such points, we're fine. So now we're coming to the unrealizability, or the upper bound, right? So in this 2-dimensional space, you know, unrealizable dichotomies for 4 points are the following, right? If you have 4 points, you know, so you cannot realize the 4 points if you have such a dichotomy. For example, this one, you know, you cannot find hyperplanes, right? That separates them. It's just impossible, right? And now here, also, you cannot just find a hyperplane that separates them, right? So you would always make a mistake, right? You would make a mistake, something like that, okay?
So would we say the same argument that there exist 4 points that we can shatter?
Well, no, it's not existence, right? It means for any 4 points, no matter how you arrange them, no matter, you know, which 4 points, you just cannot shatter them. Does that make sense? So let me see in the chat. So people are saying in the case of the real line, H equals to H1, H2, H3, H4. Actually, that's not true. Let me clarify that. In the case of, you know, interval real line, I'm just showing examples of H. So it is not true, right? It is not true that H equals to H1, H2, H3, H4 set, right? Otherwise, then this is a finite hypothesis class. Actually, I'm just saying H1, H2, H3, H4 are just an element from hypothesis class H. But this H includes every possible interval of the real line. Okay. Okay. Does this make sense? Okay. So now what is H here in this hyperplane? In this hyperplane, it, you know, for example, this is H1, right? This is this hyperplane. Well, it look like a line here because you're in a 2-dimensional space. But if you imagine in a higher dimensional space, it's going to be a hyperplane. Okay. So this is H1, right? And, you know, you can imagine I can have H2. Again, you know, all these H1, H2, H3 are elements of your hyperplanes, but you have infinite, you know, number of hyperplanes in your space, you know, 2-dimensional space, right? Any, you know, so in a 2-dimensional space is just a line. So you have infinite, you know, lines. So all of the lines are going to be your hypothesis. Okay. So, you know, so basically, you know, you're characterizing how rich the lines are in terms of, you know, classifying my data into positive and negative examples, right? So, you know, I'm saying it is not very rich because in this example here, if I have 4 points like this, and each of them should have been labeled as this one plus, this one minus, this one plus, and this one minus. If I do that, so apparently I can't find any line that separates them in the way that one side of the line is positive and the other side of the line is negative, right? So that's what I mean by my VC dimension cannot be 4 in this scenario. Actually, if you think about it more carefully, for any hyperplane in a d-dimensional space, the VC dimension is going to be d plus 1. So in a 2-dimensional space, it's going to be 3. Okay. Any other questions? Well, don't be shy. I mean, especially if this is the first time you are using Rademacher, VC dimension, and you're, first time learning these concepts, it could be very confusing. And, I'm happy to discuss more about it. Okay, if not, I will continue. Laura, do you have a question? Okay.
Yeah, so I'm just like staring at the slides, but like to prove that it's unrealizable, do you just have to find an example? Like in this case, it's how many points? Do you just have to find an example where there's no set of hypotheses that shatters the data?
That's not true. Actually, you have to make sure that, even it's not about existence. It's about you cannot find any 4 points that can be shattered by H.
Okay, and it's hard to show that it's unrealizable because it's
you cannot prove by enumerating all possible ways of finding all possible arrangements of 4 points, right?
Yeah.
But this is a simple argument to see, as you can imagine.
So is that why like proving unrealizability, is that why it's hard?
You can prove by contradiction. So I don't want to provide proofs here because this is a rather intuitive argument.
Okay, that makes sense.
Okay, I'm gonna move forward if no other questions. Okay. All right, so now, this is the first hypothesis class we've learned is axis-aligned rectangles in the plane, which caused a lot of confusion, I understand. So what is the hypothesis H, right? So in this scenario, the hypothesis H is just every possible axis-aligned rectangles. In the space, okay? So in this scenario, we're actually looking at a 2-dimensional space because if you think about the d-dimensional space and looking at like a polygon kind of thing, it's a little bit more complicated, okay? So we're looking at a 2-dimensional space. We're looking at a rectangle, axis-aligned rectangles. So for any of the hypotheses first, it is easy to see that if you have 4 points, okay, so then you can always find rectangles that can realize the dichotomies. For example, if you have these 4 points, let me use my cursor here. So you have these 4 points, okay? So one way of labeling these is, for example, these 2 are positive and these are negative. Then you can find such a box, right? So this is axis-aligned rectangle. So you cover like these negative points. So the negative points are within the rectangle, whereas the positive points are within the rectangle and negatives are outside of the rectangle. And similarly, if you have this way of, labeling, then, this box will cover that. This way, this box will cover it, and this way of labeling, this box will cover it. Okay? So you can verify, essentially, I'm not verifying for all possible ways of labeling, but, you see basically what I mean, right? So you can verify for all possible ways of labeling. It essentially, you have like 2 to the power 4 ways of labeling. Just need 16 ways. All right. So this is going to be a lower bound. Now we're talking about non-realizability. Well, so this example, I hope this is intuitive enough for you to understand why you can never shatter 5 points. Right? So no set of 5 points can be shattered. Label negatively the point that is not near the sides. Okay, so this is how we're doing it. So, you can always find a labeling that is contradicting with your hypothesis. So I'll let you think a little bit about it.
I had a quick question. So for example, the points, like in the first part, the points have to be oriented like that, or like, for example, in that second one, couldn't you slide the negative to the left and inside of the 3 positive signs?
Okay, so if you do that, so are you saying, so you can tell me so you're basically saying if I have 4 points like this, then you can realize it. Okay, so now I'm gonna ask you again, can you remember when we're talking about lower bound, we're talking about existence?
Yeah.
Okay, so apparently this is not a good example because it cannot be fully shattered. This sample cannot be fully shattered, right? The way of ranging these 4 points. Yeah, I agree with you. However, I'm trying to justify that if you arrange the points in this way, what I'm showing in these examples, then you will have a fully shattered.
Got you. Okay.
Yeah, so again, this is about existence rather than, non-realizability. However, what you just asked was a very good way of explaining this non-realizability, right? So let's say you have, you just arrange the 4 points to be on a box, okay? So like to be exactly on, aligned with the axis aligned rectangles. So if you have to, shatter like this positive label of these 4 points, then you have to use a rectangle like this, right? However, if you arrange the 5th point within this, then you cannot realize this dichotomy, like this positive, and negative here. So that's essentially why we say no set of 5 points can be shattered.
I have a quick question. What if you arrange the 5 points in a form of a pentagon?
Can you say that again?
What if we arrange those 5 points in a form of a pentagon, like 5 vertex of pentagon?
What is?
Then we can draw like a rectangle such that we can put all the positives in.
Okay, so yeah, so again, let's come to this, right? So okay, so how should I say this? So it means no set of size d plus 1 can be shattered by h. Is that what you? I couldn't answer your question. Maybe someone can help me understand the question.
I have the
Instead
same
of arranging
question.
first 4 points by a rectangle, and then if you arrange the 5th point, we may not be able to shatter. Instead of that, if we arrange all 5 points in the form of a pentagon, sometimes we may be able to shatter.
I don't know if I follow the question.
I think what he's saying is, what if we moved the negative value outside of the axis aligned rectangle? Then it would technically still be accurate. And if, since we can do that, does that make this shatterable?
Okay, so then we only have to ask a question, you know, if we find such a 5 points, can we fully shatter these 5 points, no matter what kind of, you know, realizations of labelings we have, right? So now is this fully shatterable?
I mean, if we arrange in a form of a vertex of a pentagon, not like this.
I think in the form of the pentagon, it's still not shatterable, but the proof doesn't work about points near the sides.
Okay.
It just like requires a different proof. Because if you label 4 of the points as positive.
Yeah. So this one, I think, you know, this is not a proof, right? This is not a proof. I think this is providing an argument telling you, you know, why in this example, you cannot fully, it's not shattered. However, you need another proof. So like I said, the proof is very tricky, right? So you have to prove that no set of 5 points can be shattered.
Yeah, that makes sense. I think it might just be confusing to have like, to show that its existence on the slides for both.
So, you know, we cannot really show the non-existence real time in class. So if you guys are interested, you can think about it. Now you know how to do, right? You can just draw 5 dots on the plane, in the 2-dimensional space, no matter how you arrange them, right? So you can just, you know, look at all ways of labeling them. So it's going to be 2 to the power of 5, 32 ways of labeling them. And you can, you know, just see whether you can draw as axis aligned rectangle to, you know, making sure that all the positive points are within the rectangle and negative ones are outside of the rectangle. Okay, so it's just very interesting exercise. If you have time, maybe after class, you can try to play with that. Okay.
That's good.
All right, so now the 4th example is the convex polygons in the plane. Now, this one is a little bit tricky, right? So the observation basically is that if you have 2D plus 1 points on a circle, then it will be shattered by a D gun, okay? So the point, you know, basically you're looking at these 2 examples, you'll see why. So if you have positive points smaller than negative points, then you can do something like this. Okay, so you're going to cover, of course, this, you know, as a little bit not precise, the figure, you should have like do something like this, you know, to cover the positive points, but, you know, basically the visualization is a little bit misleading. So you can just cover this positive ones using a D gun, right? And now, if the positive points are greater than negative points, then what you can do is you can just, you know, draw this T-gun so that, you know, each of the negative ones are outside. So again, this visualization is a little bit confusing, but, you know, you have something like, you can always find a line so that the negative ones is outside of the line, you know, on the other side of the line, and the positives are on this side of the line. So basically, because we only require existence, so as long as you find points, 2D plus 1 points on a circle, we know that it will be shattered by a D gun. So your VC dimension is at least greater than or equal to 2D plus 1. Okay, so now the question is, you know, can we show that no points of 2D plus 2 can be shattered by D-gons, right? So actually, again, we don't have a proof here, but it can be shown that choosing the points on the circle maximizes the number of possible dichotomies. Okay, so that's what they can tell you as a fact, but I didn't provide a proof here. So essentially, the VC dimension is actually 2D plus 1 for a convex polygon in the plane. Okay. Oh, sorry, I didn't mention it's D, so it has to be D-gon. If it is just a, any convex polygon, it's actually infinity. As you can imagine, no matter how you arrange the points, and no matter how you label the points, I could always find a convex polygon that's making sure all the positive ones are within and negative ones are outside. Okay, so let me see if there is anything interesting or if there is any important things that we can discuss from the chat. So which one should I look? Oh, okay. So I think you're talking to each other and it seems like you've resolved your problem, right?
Yeah, thank you. I got it.
Yeah, okay, great. So any other questions?
So when it says VC dimension equals infinity, so we can pick infinity number of points, and then we can find a polygon that shatters those points.
Yeah.
So
but
let's say
the polygon is not a D polygon, right? It is
right.
Polygon, you can say.
So let's say that you're on R2 and the points you choose are every point on R2. So can you make an infinite polygon that shatters every?
Yeah, in theory, you can. Yeah. But again, you cannot compare things when they are infinity. You have infinite points, but the polygon can also have infinite line, the edges, right? Okay. So another example, I'll very quickly go through the sine function. So indeed, the observation is that any finite set of points on the real line can be shattered by the sine function of this form. So the sine function would map t to omega t, where omega could be any real number. Okay, so this is the so-called hypothesis set, right? So this is your H. Apparently, your H allows any choice of omega here. Okay, so you can see omega basically, kind of help you to understand the frequency of, this periodic function, right? So, how frequently it goes back to its original value. So it is a periodic function. And also you can see, for instance, you have these points, positive ones are blue and negative ones are red. And you are always able to cover those blue ones inside the sine function, right? So you can imagine these are inside the smaller than the sine function, but the red ones are always greater than the sine function. Okay. So actually the sine function is a very rich function that can characterize, that can shatter all possible dichotomies of the points in the plane. Okay. Well, Wei-Ming asked an interesting question. If we have an infinite number of points, the polygon you choose would become a circle. Well, that is actually true, I think, right? Because if you think about it, the edges will be like narrower and narrower. Essentially, asymptotically, it become like a circle, I think. Yeah. I don't know if people agree with me, but I think that's correct. Okay, so now, you know, we were done with the sign function. Any questions? If no, I think we will move on to generalization bound of VC dimension, which is, again, a very simple extension from the previous generalization bounds. Okay. So generalization of VC dimension, this is going to be commonly used, you know, in your, maybe in your research, right? Maybe you will replace the VC dimension with your covering number. But so the probability that your true error will be upper bounded by your empirical error plus this generalization gap will be very high, so close to 1. However, this generalization gap depends on the number of examples as well as the complexity of your hypothesis class. Okay, so you can imagine a neural network has a higher hypothesis, has a higher complexity, VC dimension, let's say. Whereas a linear classifier, essentially, you know, remember what is the VC dimension of a linear classifier? D+1, okay? So you can imagine the, you know, the VC dimension D here is very different for different hypothesis class. Therefore, in order to achieve the same amount of generalization gap, you would need different number of examples in your training data set. Okay, so that's why you are unlikely to overfit for a linear classifier, but you are more likely to overfit for a neural network if you use the same number of examples, right? This comparison is only making sense if you are comparing under the same number of examples when you're doing training. Okay, so M is equal. Now, so that's gonna be the last slide about the complexity of the infinite hypothesis class and the generalization error or generalization error bound on this infinite hypothesis class. We will have a chance to review some generalization kind of bounds for neural nets, but that would be after our lectures on boosting. So this is probably a good time to review or you know, to ask questions. You know, any questions you have in terms of generalization, in terms of how you think about overfitting, in terms of how you think about sample complexity, how you think about a trade-off between sample complexity and, you know, the hypothesis, the size of the hypothesis class, right? You know, how to characterize the richness of the hypothesis class.
So I have a question.
Yeah.
So, I mean, so usually is computing the VC dimension usually something that's doable to the point where one could derive this bound?
Well, so yeah, usually VC dimension you can, but the thing is sometimes it's just not necessarily a good way of characterizing the complexity. You will see an example in homeworks, actually. I don't know if we posted that homework, but you will see an example in homework and you will see what I mean.
Oh, okay. Thanks.
Yeah, no problem. Okay. Well, so now I hope we've got a quantitative understanding of sample complexity and pack learning, probably approximately correct learning, gained like a good understanding of overfitting issues in machine learning. I mean, these are very important concepts in learning theory. Well, now I'm going to switch topic. It's actually not exactly switching topic because the generalization ability and how we characterize, you know, the realizable versus non-realizable cases, and how we, you know, evaluate the errors made on these, you know, classifiers or these hypotheses. You know, we will still talk about those concepts that we're already talking about, but now we are going to, you know, not specifically focusing on generalization or characterizing complexity, but we're going to think about an algorithm. So what is this motivation of this algorithm? This algorithm is an ensemble algorithm. Many of you have heard about it. Basically, the idea is if you have weak classifiers, what is weak classifiers? You might have some really weak ones that can only do a little bit better than random guess, right? Let's say you have a binary classification problem. Your accuracy is like 51%, okay? So you are really doing very bad using these base classifiers. However, if you can continuously getting new ideas or, you know, fresh ideas from these classifiers, right? So you have one classifier which gives you 51% accuracy, another classifier which gives you, you know, 50.2% accuracy, and so on. So as long as you have enough draws, you draw wisdom from many base better than random hypotheses, you will get a very strong hypothesis, and you will get a very strong classifier. Indeed, the complexity of the classifier could be arbitrary. However, we do find a surprising result when we're doing experiments is that when we're doing these kind of ensemble methods, although theory might say it is very complicated because, you know, my hypothesis can be arbitrarily complex, but it is resistant to overfitting. So this is a really, really appealing property we're observing here. So can we understand why? First of all, can we understand why doing an ensemble of a lot of weak classifiers could give you a good result? Now, secondly, can we understand why it is resistant to overfitting? So in the next few lectures, hopefully, you know, 3 lectures or so, we wanted to discuss this so-called adder boost. So it is an ensemble method that has theoretical desirable performance, which requires base classifiers to be slightly better than random. Okay, so we also have a project that is related to this, is, you know, understanding certified defense through boosting. Okay. Okay, so first I wanted to introduce this concept of weak learning. What do I mean by weak learning? So the definition of the weak learning is you have a concept class C. Okay, so the weak learning is with respect to a concept class. Okay, so if the concept class is weak learnable, only if there exists a weak learning algorithm L and a gamma greater than 0, such that for any delta greater than 0, and for any hypothesis, for any target concept within that concept class, and for any distribution, your probability of actually, so, you know, I'm talking about probability here, but I'm essentially evaluating this one. Okay, so first I'm evaluating the true error of HS. Okay, so it is smaller than equal to 1/2 minus gamma, and then I'm taking the probability over this, you know, the random variable S, the sample. So as long as this probability is greater than equal to 1 minus delta, and then, you know, you also require the M to be polynomial in terms of 1/delta for a fixed polynomial. Okay, so basically if you satisfy this, then it is PAC learnable. So how can we digest this, right? So first of all, we can see this is about a concept class, right? It's a property of the concept class. It means that this concept class is just weakly learnable, right? So we can always find such hypothesis so that, with high probability, the true error of these hypotheses is gonna be smaller than something a little bit smaller than half, right? So it is still, better than random guess, right? Basically. Okay. Is there any question? Okay. So now what's the boosting idea? The boosting idea is you find simple and relatively accurate base classifiers, often not very hard. Okay, so, like cloud sourcing, right? You might imagine that you don't, experts are very expensive, but mechanical Turks could, make mistakes. As long as they are doing better than random guesses, you can use cloud sourcing somehow smartly ensemble their results to get a strong classifier or a strong, hypothesis, right? So, you have a bunch of base classifiers, 1, 2, all the way up to n. Well, you somehow have a smart way of ensemble them. I wanted to, emphasize that we will see this is not a trivial ensemble. We have a way of smartly combine them. A trivial ensemble doesn't necessarily induce good empirical performance or doesn't induce good theoretical results. Okay, so it is a smart way of ensembling. And essentially how you design these base classifiers are also tricky. It's not a simple thing in order for you to achieve desirable theoretical performance. But anyhow, so you have these smart ways of designing these base classifiers, you ensemble them in a smart way, and essentially you get a strong learner, okay? So now the question is, how do you train these base classifiers? As I've already spoiler alerted, these base classifiers, you cannot just trivially train them. It is a little bit, it requires a little bit more care than that. Also, how do you combine the classifiers? How do you do the ensemble? Now, is there guarantee on empirical accuracy, right? So, or does it overfit? So we're going to answer all the 3 questions in the next few slides. So this is actually a very old algorithm. It's in 1999. Maybe some of you were even not born by then. So anyway, so you have a concept class C, right, which is mapping from input space to a binary label, -1, +1. Now, your hypothesis class is any labeling of these examples. So I just write it as -1, +1 for every x. So it's like any label of that. So essentially, you can label it anyhow. Now your S is, just these collection of the examples. So it's your training data set. Okay, you have M examples in your training data set. Now the base classifier are going to be an element belonging to your hypothesis class H. And you have T such base classifiers, okay? Now, I wanted to emphasize one thing, which is epsilon T. It basically means, so, although I put a probability here, it is a little bit misleading, because I'm using dt vector here. So what is dt? dt is a probability vector. You can imagine this is like a weight you put on each of these M examples in your sample. Okay, so that's why you have this, you know, when you calculate the epsilon t, it's essentially like this indicator function, this 0, 1 error, weighted by the dti, so the ith element of the dt. So each element of the dt is denoting how much weight you put on that example. Okay, it's like an empirical distribution on your training examples. So any confusion here? I think this one, you know, people might be confused a little bit. Okay, so dt is not a distribution really, it's an empirical probability vector. Its length is determined by the size of the sample, and each element denotes how much weight you put on that example. Okay, so for instance, if you introduce this one, you know, you might have, let's say, 5 examples, right? And your weight for these are like 0.2, 0.2, 0.6, and 0, 0. So this is your dt. So now, you know, you might have associated losses for these examples. Let's say I have a loss 1, I have a loss 1, I have a, oh, what happened? Actually, let me say I have a loss 0, I have a loss 0, I have a loss 0, and loss 1 here. Okay, so in this example, you know, I'm making mistakes on these 2 examples. But I'm not making any mistakes for these 3 examples. But when I calculate the epsilon t, you can see I actually will have a 0 error because I only care about the first 3 examples, and I'm not making any error on these first 3 examples. So this expands the way we evaluate empirical errors on a sample. We have a way of controlling the weights, in terms of how we weight the examples, in terms of calculating the empirical error. Okay? All right. So this is how boosting works. So, you know, you have, we have 5 minutes. I'm going to go through the figures. I don't have time to go through the pseudocode, but, you know, let's first go through the figures. The figures are pretty intuitive, okay? So you have these points, okay? So in practice, you have these training points. So in practice, let's say the blue ones are, you know, blue are positive and red are negative. So you have all these x, y's, right, in this space, and the y's are, you know, denoted by the color of the codes, of the dots. So these are your training data set, and it is 1 sample. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 9 examples in your training set, okay, or in your sample. So you have something like this. Then let's assume that you wanted to have weak classifiers that are simple enough, right? Let's say linear classifiers. So you're going to generate a line so that you can separate as best as you can these blue points and the red points. So it turns out if you do that, you find such a line here. Okay, you find a line here, and this is gonna be called H1. Okay, so this is, let's say, your linear classifier here. Well, now, so any questions so far? Okay, so now what's going on is, like, you know, this is the first base classifier. Now, when you look for the second base classifier, instead of putting these examples as their input to the classifier, you actually would putting more weight on the examples that you made an error. So for instance, you know, you've made an error on this one. And this one as well as this one, because you've decided to classify here as red and here as blue. Okay, so as long as you're above this line, you're going to classify all the dots as red, and you're lower than this line, you're going to classify everything as blue. This is what your H1 is doing. However, you know that I'm making these mistakes. So what happens is that next time when I try to come, to look for base classifiers, I will putting more weights on these wrongly classified examples. Okay, so why? Because I think those are difficult examples. I wanted you to focus more. So I'm telling you, look, I know you can only do better than random, but I ask you to focus on these examples that are very difficult. So pay more attention to these examples. So that's the basic idea. So if you ask the base classifier to do that, then the base classifier is gonna generate a new line here for you. Okay, so this is the weak classifier you learned using these weighted examples. So you get this line, okay? Well, so similarly, for this line, you are also making a mistake. If you are here. So if you classify everything here as red, everything here as blue, so then what happens is you're still making mistakes on these ones, okay? So now in the next round, you're saying, okay, not only you should focusing on these examples, but you should also focus on these two examples because I'm making mistakes for these two examples as well. Okay, so you have another weak classifier, you pay more attention to these harder examples, and now you get a new classifier, which is this H3 here. Okay, so imagine, of course, you can do that for t times, but here I'm only doing that for 3 times. Well, so what happens is I will have a final classifier, which becomes a linear combination of these weak classifiers. Actually, I don't have time to talk about how I select the alpha t, the linear coefficient of how to combine the weak classifiers, but it's related to how I make those mistakes on these examples. We'll talk about that later, but this is very important for the strong classifiers to be strong. But pictorially, you can see, so this is your H1, right? And this is your H2. This is your H3. So through this linear combination of H1, H2, H3, you essentially get this strong classifier here. Okay, so you can see now this alpha t is very important because if you don't select alpha t in a good way, then you might end up with, for example, this one, right? Which is not a very good strong classifier. Okay, so basically I've talked about, the basic idea behind add or boost. So you adaptively putting weights on harder examples, and you kind of combine the weak examples in a smarter way that you calculated from the previous steps. So, okay, so that's the end of today's lecture. Thank you. If you do have more questions, feel free to ask that on Piazza. Okay, thanks everyone.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Yeah, thank you.